This paper introduces Eco-AI, a set of practical methods for making generative model training more energy conscious. The focus is on diffusion-based image generation and multimodal text-to-image systems, which are powerful but expensive to train. The goal is to measure where the energy and carbon costs come from, and to show which training choices can lower those costs without hurting model performance. The authors run controlled experiments across diffusion models that range from about 200 million to 3 billion parameters. Smaller models are trained on a local machine with 8 NVIDIA A100 GPUs, and larger models are trained on a high-performance cluster with up to 64 A100 GPUs. They compare two electricity scenarios, one with about 70% renewable energy, and one with about 30% renewable energy, and they convert measured energy into carbon dioxide emissions using the grid emission factors. They also vary training duration, numeric precision, optimizer choice, and batch size, while tracking power with standard monitoring tools. The results show several clear patterns. Mixed precision, also called FP16, reduces energy use by about 15% compared to full precision, and this holds across model sizes. Carbon emissions depend strongly on the electricity mix, and can more than double when the same training run uses a lower renewables grid. Energy use grows almost linearly with training time, so long runs quickly dominate the footprint. Batch size improves efficiency up to around 64 to 128, and then the gains flatten because synchronization and memory overhead increase, especially for the largest models. The paper also highlights a trade-off between cluster training and local training, where clusters can be efficient when fully utilized and well-cooled, but can waste energy when underused and can emit much more carbon if they are located on a high-carbon grid. Based on these findings, the paper recommends a simple sustainability playbook. Use mixed precision by default. Choose batch sizes in the efficient range, roughly 64 to 128, instead of pushing larger batches that do not pay off. Prefer cleaner energy when you can, by selecting low carbon regions or scheduling jobs when renewable power is more available. Treat the optimizer as an energy choice, since some options converge faster but can cost more energy per step. Reduce wasted compute with early stopping, adaptive learning rates, and checkpoint-based fine-tuning, and rely on transfer learning whenever possible, since fine-tuning can cut energy dramatically compared to full retraining. Finally, the paper calls for future work that links model quality to emissions, tracks data center efficiency more precisely, and explores training methods and hardware that reduce energy per computation.